Two particles separated by the entire width of the observable universe can affect each other instantly, and Einstein spent the last 20 years of his life trying to prove that was impossible. He failed. In 2022, physicists Alain Aspect, John Clauser, and Anton Zeilinger won the Nobel Prize in Physics. Not for a theory, not for a thought experiment, but for experimentally proving that two particles, once connected, remain connected across any distance with zero time delay, in direct violation of everything classical physics said was possible. That prize was the world's most prestigious scientific institution, officially acknowledging something that sounds like science fiction: the universe is non-local. And once you understand what that actually means, nothing about reality will look the same again. By the end of this video, you are going to understand three things that most people, including most physics graduates, have never sat with long enough to feel the full weight of. First, you will understand exactly what quantum entanglement is and what it definitively is not, because almost everything you have been told about it is either incomplete or misleading. Second, you will understand why the 2022 Nobel Prize experiment didn't just confirm entanglement. It mathematically closed the door on every rational alternative explanation, including the ones Einstein preferred. And third, the one that will sit with you long after this video ends, you will understand what it actually implies about the structure of reality itself, about space, about time, about whether you are more connected to the universe than your skin suggests. Stay with me, because the last part changes everything. I want you to do something right now. Hold up your hand. Look at it. Really look at it. Not the concept of a hand, not the word hand, but the actual physical thing you are seeing. The skin, the lines, the slight translucence at the fingertips if the light catches it right. That thing, that object feels completely solid, completely local, completely here. It feels like it exists independently of everything around it. It feels like it has a definite position, a definite state, a definite boundary where you end and the air begins. That is how reality feels. That is how every human being who has ever lived has experienced reality, as a collection of separate things, in separate places, doing separate things, connected only when something physically travels between them. A sound wave, a light photon, a hand touching another hand. Cause and effect, always local, always with a speed limit, always bound by the laws of space and time as Newton understood them and as common sense demands. Now here is the question, and I need you to hold it in your mind for the next several minutes, because we are going to come back to it. What if that feeling of separateness, that fundamental intuition that things exist independently of each other in their own definite places with their own definite properties, what if that is not a fact about the universe, but a feature of the scale at which you happen to exist? What if at a deeper level, the level where the universe actually writes its own rules, nothing is truly separate from anything else? What if your hand right now is entangled with particles on the other side of the cosmos, and the only reason you do not feel it is because you are too big? To understand what is actually happening here, we need to go back to the beginning. And I mean the actual beginning of this problem, which starts not with a particle accelerator or a laser laboratory, but with an argument between two of the most brilliant minds in the history of science, conducted almost entirely through letters and journal papers across decades about the deepest possible question: what is real? The year is 1935. Quantum mechanics is barely a decade old, but it is already producing predictions of startling accuracy. Experimenters are confirming its equations again and again, and yet one of the architects of modern physics, Albert Einstein, is deeply, viscerally uncomfortable with what those equations actually say. Not because they are wrong, because of what it would mean if they were right. Einstein, together with Boris Podolsky and Nathan Rosen, publishes a paper that year, known ever since by their initials as the EPR paper, and the argument in it is elegant and devastating. It goes roughly like this. Quantum mechanics says that certain properties of a particle, its spin, its polarization, its position, do not have definite values until the moment you measure them. They exist in what physicists call a superposition, a genuine simultaneous combination of multiple possible states, not just unknown but undetermined, hovering in a kind of mathematical fog until an observation forces a choice. That is already strange. But here is where Einstein's fury really begins. Quantum mechanics also says that two particles can become entangled. And entanglement means this: when two particles interact in the right way, their quantum states become mathematically linked. They share a single quantum description, a single wave function, as if they are no longer two objects but one extended system. And here is the devastating part: that linkage does not break when you separate the particles. You can take one particle to the far end of a laboratory. You can take one particle to the moon. Theoretically, you could take one particle to the edge of the observable universe. And the moment you measure one particle, the moment you look at it and force it to choose a definite state, its entangled partner, wherever it is, instantly reflects that choice. Not after the information travels. Not with a tiny delay. Instantly. With zero time elapsed, Einstein called this spooky action at a distance, and he did not mean it as a compliment. He meant it as a reductio ad absurdum. He was saying this prediction from quantum mechanics is so absurd, so obviously impossible, that it must mean quantum mechanics is incomplete. There must be, he argued, hidden variables, real definite properties that particles carry with them all along, properties that quantum mechanics simply has not found yet. The way a coin has a definite heads or tails, even while it is spinning in the air and you just cannot see which. The particles are not truly undetermined, Einstein insisted. They have secret instructions, pre-written answers. And when we measure one, we simply read the answer it was already carrying. No spooky action required. No information traveling faster than light. Just ordinary physics we had not measured precisely enough yet. This was not a fringe position. This was Albert Einstein. And for nearly 3 decades, there was no way to tell who was right, because no one had designed an experiment precise enough to distinguish between Einstein's hidden variables and genuine quantum spookiness. They made the same predictions in every test that existed. The two models were experimentally indistinguishable. Then in 1964, an Irish physicist named John Bell did something extraordinary. He sat down with a pencil and paper, and he proved, mathematically, rigorously, inescapably, that the two models were not equivalent. That if you designed the right experiment, measuring entangled particles in a specific way, under specific conditions, the hidden variable model and the quantum model would produce measurably different results. Bell derived an inequality, a mathematical boundary, and he showed that if Einstein was right, if particles carry hidden instructions, then the correlations between entangled particles can only ever be so strong. There is a ceiling, a limit, a number, and if the measured correlations exceeded that number, if the particles were more connected than any set of pre-written instructions could explain, then Einstein was wrong. Hidden variables were dead, and the universe was genuinely irreducibly strange. Bell's theorem was the most important thing anyone had written in the foundations of physics in 30 years, and almost nobody paid attention to it for nearly a decade, because testing it required technology that barely existed. You needed a source of genuinely entangled particles. You needed detectors fast enough and precise enough to measure them reliably. You needed to be able to change the measurement settings quickly enough that the particles could not, even in principle, have coordinated in advance. It was a staggering experimental challenge. Alain Aspect tackled that challenge in Paris in the early 1980s. His experiment was meticulous. He used entangled photons, particles of light, generated in a calcium atom source. He measured their polarization states, essentially which direction they were oriented, using detectors on either side of the apparatus, separated by enough distance that no signal traveling at the speed of light could possibly pass between them during the measurement. He switched the measurement settings randomly, fast enough that no pre-existing hidden variable could have anticipated the choice. And then he ran the experiment thousands of times and looked at the correlations. What he found was this: the particles were more strongly correlated than any hidden variable model could ever produce. Bell's inequality was violated, decisively, unambiguously. The correlations exceeded Einstein's ceiling, not by a little, but by a lot. And the only explanation that fit the data was the one Einstein had spent his career rejecting. The particles were genuinely entangled, genuinely sharing a quantum state, and measuring one was genuinely and instantly affecting the other, regardless of the distance between them. But, and this is crucial, Aspect's experiment still had what physicists called loopholes. Not because the result was wrong, but because experimental imperfections left tiny logical gaps that a committed skeptic could slip through. Maybe the detectors were not quite efficient enough. Maybe the random number generator used to switch settings was not truly random. Maybe there was some subtle local influence nobody had accounted for. These loopholes were not excuses, they were rigorous scientific standards. And over the following decades, experimenters around the world worked systematically to close them one by one with better technology, tighter protocols, more sophisticated designs. By 2015, the loophole-free Bell test had been achieved, first in Delft, then in multiple independent laboratories. Every loophole simultaneously closed. Every alternative explanation simultaneously eliminated. The correlations were still there, still exceeding Bell's boundary, still impossible under any locally realistic model of the universe. And in 2022, Aspect, Clauser, and Zeilinger, the three physicists whose work built this entire experimental edifice over 50 years, were awarded the Nobel Prize in Physics. The citation was explicit. They had provided experimental tools to test the nature of quantum entanglement and demonstrated the violation of Bell inequalities, which is the scientific establishment's precise, restrained way of saying they proved Einstein wrong. They proved the universe is not locally real. They proved that two particles, once entangled, are connected in a way that transcends space. Now I need to be careful here, because this is the point where popular science almost always makes a critical mistake, and I do not want to make it. The non-locality of quantum entanglement does not mean information travels faster than light. You cannot use entanglement to send a message. And here is why. When you measure your particle and it collapses to a definite state, your partner's particle also collapses, but your partner does not know what state their particle is in until they actually measure it, and their measurement result looks completely random. A 50-50 shot. It is only when you compare notes, when you communicate through a classical channel, a phone call, an email, some signal that moves at or below the speed of light, that you discover the correlations. That you see that your results and their results, while each individually random, are correlated in ways that should be impossible. The non-locality is real. The faster-than-light communication is not. The universe seems to have engineered this precise loophole, allowing genuine non-local connection, while still preserving the cosmic speed limit in a way that prevents paradox. But do not let that technical caveat shrink the enormity of what has been demonstrated, because what the Bell experiments prove is not merely a quirk of subatomic particles. They prove something foundational about the architecture of reality. They prove that the universe, at its deepest level, is not made of separate things in separate places with separate independent properties. They prove that locality, the assumption that a thing is only directly affected by what is immediately next to it, is not a law of nature. It is an approximation, a very good one at the scales of everyday life, but not a truth about the universe as it actually is. The universe, at its most fundamental level, is a single non-local system, and the particles you are made of were once close enough together, in the first moments after the Big Bang, to have been entangled with everything else. Which raises a question so enormous I almost hesitate to say it out loud. Are you still? Here's what I keep coming back to, in the quiet after reading the Bell experiment papers. The universe did not have to be this way. Einstein's universe, the one he spent 20 years trying to defend, was a universe of genuine separateness, where things existed independently, where a particle on one side of the cosmos had no immediate relationship to a particle on the other, where reality was a collection of distinct, local, self-contained facts. That universe would have been comfortable. It would have confirmed what every human nervous system already tells you, that you are here, and the rest of the universe is there, and the space between you and it is real and deep and unbridgeable except at the speed of light. But the universe chose differently. The experiments say clearly, not metaphorically, not philosophically, but mathematically and empirically, that two things can be separated by billions of light years, and still be, in some sense that our language does not have good words for, the same thing. That space, the thing we use to define separateness, does not do the job we assumed it did. And if space does not create genuine separateness, then the boundary you feel between yourself and everything else, the skin, the skull, the silence between your thoughts and the world, may not be as fundamental as it seems. You are not a separate object moving through a universe. You are a localized process within a system that has never been divided. The question is not whether you are connected to the universe. The question is whether you ever stopped being it. So let me close the loops I opened at the beginning, because I made you 3 promises, and I intend to keep every one of them. I promised you that almost everything you have been told about quantum entanglement is either incomplete or misleading. And now you have enough context to see exactly why. The popular version of entanglement that circulates online, in documentaries, in casual science communication, goes something like this. 2 particles are linked, so when you measure one, the other one knows instantly. And that description is not wrong exactly. But it is structured in a way that almost inevitably leads to a misunderstanding, because it implies that information is somehow jumping between the particles, that there is some invisible wire, some quantum telephone cable connecting them across the void. There is not. The connection is not a transmission. It is a correlation that was baked into the system at the moment of entanglement, and that cannot be broken by distance, cannot be degraded by time, and cannot be explained by any model in which the 2 particles are genuinely separate things carrying independent properties. The entanglement is not a signal that travels. It is a structure, a feature of the wave function, which is the mathematical description of the system, that reveals itself when you make a measurement on either part of the system. Think of it this way. Imagine you have a pair of gloves, and you separate them without looking, put one in a box, and mail that box to someone on the other side of the world. The moment they open the box and see a left glove, they instantly know you have the right glove. That looks like instant information transfer, but it is not. The information was determined when the gloves were separated. Einstein believed entanglement was like the gloves, predetermined, locally real, carrying hidden information that we simply had not read yet. Bell proved that it is not like the gloves. The glove analogy breaks down precisely because gloves have definite handedness all along, whether you look or not. Entangled particles provably do not. Their properties are genuinely undetermined until measurement, and yet they are still correlated beyond what any predetermined instruction set could produce. That is the thing the Bell test actually measured. Not just that they are connected, but that they are connected in a way that is impossible if they are separate things. The distinction matters enormously, because the glove model preserves a local reality, a universe in which things exist independently with definite properties. The Bell violation destroys that model. Not dents it, not complicates it. Destroys it. What replaces it is a universe in which the deep structure is non-local, in which things that have interacted are not, in any fundamental sense, separate thereafter, no matter how much space you put between them. That is not a metaphor. That is the experimental result. That is what the 2022 Nobel Prize was awarded for confirming. I promised you that the 2022 Nobel Prize experiment did not just confirm entanglement. It mathematically closed the door on every alternative explanation, including the hidden variable theories Einstein preferred. Let me show you exactly how completely that door was shut. The history of Bell testing is, in a sense, the history of loophole closing. Every loophole represented a possible escape route, a way a classical local model of the universe could, in principle, have reproduced the quantum correlations without requiring genuine non-locality. There were three main ones, and I want you to understand why each of them is now permanently gone. The first was called the detector loophole, or sometimes the fair sampling loophole. The problem was this: particle detectors are not perfect. They miss some particles, and a sufficiently clever critic could argue that the particles being detected are not a fair sample of all the particles generated, that the experiment is somehow selecting for the correlated pairs while missing the uncorrelated ones in a way that makes the correlations look stronger than they really are. Closing this loophole required building detectors efficient enough that they caught a large enough fraction of the particles that this selection argument became mathematically untenable. It required years of engineering progress in photon detection technology. But it was closed. By the time of the definitive experiments, detector efficiencies were high enough that the fair sampling argument was ruled out completely. The second was the locality loophole, the most important one, and the one Aspect's original experiment addressed but did not fully close. The problem is this: if the measurement settings on the two detectors are not changed fast enough, there is a theoretical possibility that some signal, some influence, traveling at or below the speed of light, could communicate between one detector and the other during the measurement window, allowing the particles to coordinate their responses in a way that mimics quantum correlations without requiring genuine non-locality. Closing this loophole requires separating the detectors far enough apart and switching the measurement settings fast enough that no light speed signal could possibly connect them. It requires precise timing. It requires random setting choices made close enough to the measurement event that no local conspiracy could have anticipated them. This was achieved, definitively, in the 2015 Delft experiment by Ronald Hansen's group, which combined detector efficiency improvements with locality closure simultaneously, for the first time in history. The two detectors in Delft were separated by 1.3 kilometers. The settings were switched randomly by a quantum random number generator. The measurement window was short enough that the light travel time between detectors exceeded the measurement time. Any local influence was physically impossible, and the Bell inequality was still violated. The third loophole was called the freedom of choice loophole, sometimes called the setting independence loophole, and it is the most philosophically radical one. It asks, what if the random number generators used to choose measurement settings are not truly independent of the particles being measured? What if there is some common cause, some shared influence in the past, that correlates both the particle states and the measurement settings in a way that mimics quantum correlations without requiring non-locality? This sounds almost conspiratorial, but it is a logically valid concern in a rigorous experimental framework. And closing it required going to extraordinary lengths, including, in one remarkable 2018 experiment called the Big Bell test, using the choices made by over 100,000 human volunteers, pressing buttons on a smartphone app as the random setting inputs, on the grounds that human free choices are, at minimum, harder to correlate with particle states than any algorithm. The correlations persisted. In another approach, experimenters used the polarization of light from distant quasars, objects billions of light years away, whose light left them long before humans or even Earth existed, as their random number sources, pushing the common cause argument back to the first seconds of the universe. The correlations persisted. Every loophole, one by one, was closed. And what remains, the inescapable residue after every alternative has been eliminated, is genuine quantum non-locality. The universe is entangled. And it knows no distance. I promised you that the last part would change everything. And I want to try to deliver on that as precisely as I can, because this is the place where it is easiest to either overreach into mysticism or underreach into dry technicality, and I want to walk the exact line between them. Here's what the Bell experiments actually imply. Not what I think, not what feels poetic, but what follows logically from accepting the experimental results at face value. If the universe is genuinely non-local, if entangled particles separated by any distance remain instantaneously correlated in a way that cannot be explained by locally predetermined properties, then one of three things must be true. The first option is that realism is false. Particles do not have definite properties independent of measurement. The moon is not there when nobody looks, as Einstein refused to believe. Physical properties are not pre-existing features of an independent external world. They are in some sense brought into being by the act of observation. This is the Copenhagen interpretation's territory, and it is deeply uncomfortable because it seems to make the existence of an objective reality contingent on observation, which raises the immediate question of what was doing the observing before there were any observers. The second option is that locality is false. There is a real objective world with real definite properties, but it is not local. Distant parts of it genuinely affect each other instantaneously. This is David Bohm's pilot wave theory, which reproduces quantum predictions exactly, and maintains a deterministic objective reality, but at the cost of requiring instantaneous non-local influences to thread through the entire cosmos at every moment. The universe in this picture is a single interconnected whole in which everything is constantly acting on everything else, with no delay across any distance. The third option is what physicist Anton Zeilinger, one of the Nobel laureates, and others have described as a kind of relational reality. The idea that what we call properties of particles are not intrinsic features of the particles themselves, but features of relationships between systems, including the relationship between the system being observed and the observer. In this view, there is no single objective reality that exists independently of all possible perspectives. There are only perspectives, only relationships, only the correlations between interacting systems. Reality is not a thing. It is a web of relationships, and those relationships are non-local. All three options have something important in common. They require us to abandon the intuition that reality consists of separate, independently existing things with definite properties, located in definite places, influencing each other only through local contact. That intuition, so powerful, so convincing, so deeply wired into the human nervous system, is not a truth about the universe. It is an emergent approximation. It is what the universe looks like when you are made of 100 trillion cells instead of a single quantum particle. And now let us think about you for a moment. The atoms in your body have a history. They were forged in the cores of stars that exploded billions of years before the Earth formed. Before that, in the first seconds after the Big Bang, all the matter and energy in the observable universe was compressed into a space so small that every particle was close enough to every other particle to interact, to exchange quantum states, to become entangled. The universe was, at its beginning, a single quantum system. Everything that has happened since, every expansion, every collision, every star, every life, is the unfolding of a system that began as one. Does that mean you are still entangled with the rest of the universe? Technically, entanglement is extraordinarily fragile. It breaks through interactions with the environment, and the warm, wet, crowded biology of a human body is about as decoherence hostile an environment as physics can produce. The kind of long-range cosmic entanglement that the popular imagination finds romantic is almost certainly not the mechanism connecting your consciousness to the Andromeda galaxy. But that is not quite the point. The point is this: the assumption of separateness, the foundational assumption that you are here and the rest of the universe is there, has been tested with equipment, with lasers, with Nobel Prizes attached to the results. And it failed. The universe, at the level where it writes its own rules, does not organize itself into genuinely separate things. It organizes itself into a single non-local system that produces the appearance of separateness at the scales where human beings happen to live. Separateness is the approximation. Connection is the ground state. And if that is true, if the most rigorous physics we have ever done points toward a universe whose deepest feature is not division but unity, not locality but entanglement, then the question is not whether it changes how you think about particles. The question is whether it changes how you think about everything else. And that leads to something even stranger. Because if the universe is non-local, if space does not create genuine separateness, then the next question is whether time does. Whether the past and the future are as divided as we assume. Whether there are experiments, real experiments, already conducted that suggest the answer to that question is also no. That is exactly what we are going to explore next time. If you believe reality is stranger than it looks, subscribe. We post one proof every week. And drop your answer below. If the universe is fundamentally non-local, if separateness is the illusion and connection is the ground state, what does that mean for the boundary between you and everything else? Is that boundary real? Or is it just the scale at which you happen to exist? I read every single one.